All right, welcome everyone to another interview of the ISQG. Today with Tadashi Takayanagi. So welcome Tadashi, and thank you for accepting the invitation.
Thank you very much for inviting the interview.
It's very nice to have you here. So to give a bit of a background, you did your PhD in Tokyo University. After that, you did a couple of postdocs at, among others, Harvard and the Kavli Institute for Theoretical Institute at the University of California. You're currently a professor at Kyoto University, and you have a visiting position at the Kavli Institute. Now you've won several prizes, but I guess one that stands out is the 2015 New Horizon Prize that you won for your research on holographic entanglement entropy. So I'm maybe 8 years late, but congratulations on winning the prize.
Thank you so much.
It's very nice. Now another very nice thing that I found out about is that you like to collect minerals. So what do you find fascinating about minerals?
Yeah, it's like, I mean, maybe I can show some of my collection. So by using this camera, can you see this?
Yes, I can see it.
In nature, we can find this. They are very beautiful crystals. So it's like very geometrically, very organized. And I could see some kind of microscopic organized rules inside this mineral. That's really exciting to me. And it's also stimulate my interest into basic science, especially this physics. That's amazing, yeah.
Yeah, it's very nice, very interesting. So back to physics, can you tell us a bit about what your research area is and what your research interests are?
Yes, I'm working on string theory, but especially string theory approach to quantum gravity, and especially the idea called holography and its connection to quantum information theory. Idea of holography says that if we think about some gravity theory on some universe, actually it is equivalent to some quantum system, quantum matter theory, which lives on the boundary of the universe. So this is called holography, but also actually recent developments of this connection between holography and quantum information actually suggests that this gravitational spacetime actually consists of some tiny bit of quantum entanglement. It's like collection of quantum bits or quantum entanglement. Like that means that gravity, to understand gravity, quantum information plays a very crucial role. So, for example, one of my current target of this research target is to understand Dojita space instead of anti-Dojita space. So anti-Dojita space, for anti-Dojita space, we know holography very much. This is called ADS CFT correspondence. But the next step is to understand more realistic universe, which is called one of the candidates is called Dojita space. And I'm quite interested in understand quantum gravity on Dojita space by using this idea, holography and also quantum information theory.
Yeah. Yeah, so you mentioned a lot about holography and string theory, because string theory is no longer just a theory about strings, right? It has gone very, very broad. So could you maybe shortly mention what does modern day string theory today look like and how it's related to ADS-CFT or holography?
I see. So yeah, interestingly, so these days in most of research papers written by string theorists, this string worldsheet itself don't show up so frequently. But actually, so if we want to understand quantum gravity, this idea called holography or ADS-CFT correspondence you mentioned is quite important. And actually, ADS-CFT correspondence was discovered based on string theory description, string theory argument. This is first found by 1997 by Maldacena. And in his paper, he discovered ADS-CFT in the following way. So we have some very heavy object called D-branes. Maybe I can write it here. So D-brane, like some kind of very heavy plane. And if we have a very heavy plane, many and coincident in the same position, like this, if we collect many heavy planes called D-brane at the same location, then following general relativity, it backreacts very much. And then we end up with very curved, highly curved space-time. This is actually anti-Dojita space, turned out to be anti-Dojita space. So this is one description, but for this object called D-brane actually has an interesting property that actually we can have a string. So this string theory have a string, and string can end on the brane. String can end on the brane, and this says that actually this theory with D branes actually described by theory called gauge theory. It's a quantum, typical quantum field theory, but it's a special one. It's called gauge theory. And so that suggests that this gauge theory is actually equivalent to gravity on this curved space-time called the anti-digital space. This is actually origin of ADS-CFT, and the presence of D brane is heavily relies on the string theory argument. And in that way, ADS-CFT was discovered by considering some very interesting setup in string theory. So that way, string theory and ADS-CFT is highly connected. But once we start from ADS-CFT, maybe initially we can forget about string theory. And that's the reason why many papers, for example, these days, don't talk about strings itself. But if we want to understand ADS-CFT from the beginning, definitely we need a string theory. This is the current situation.
Yeah. So yeah, you focus also on entanglement entropy. I think that's also where you're most known for. So how does entanglement entropy look like in this story of ADS-CFT, and how is it connected to string theory?
Yes. So entanglement entropy, maybe like this way. So we have is defined as a quantum correlation between two regions. Some region called A and other region called B. This region and outside. So this is a quantum correlation between two body systems, two systems, actually called entanglement, quantum entanglement. And the amount of quantum entanglement correlation is measured by quantity called entanglement entropy. So this is a very interesting quantity which can be applied to many different systems like black hole physics and also condensed matter physics and also obviously important quantum information theory. But by using this ADS-CFT correspondence, we can calculate this quantity in a very geometrical way, which I write it here. So we have this kind of anti-digital space, which I explained before. This is the anti-digital space. Anti-digital space lives here. And this is a kind of special universe, and it has a boundary here. This is a boundary here. Boundary here. And the claim of ADS-CFT is this bulk gravity. Gravity is here. This red part, we have a gravity. It actually turns out to be equivalent to some quantum system, quantum field theory, which lives on the boundary. So boundary is here. So maybe quantum field theory or some quantum matter lives on here. It's equivalent to the ADS-CFT. But if we want to calculate this entanglement entropy, so we divide this space into two parts of this field theory. So we divide this space into two parts like this. This is a region A, and outside is called B, right? And this correlation between A and B is measured by entanglement entropy. And actually, to calculate entanglement entropy, we extend this boundary towards the bulk ADS. ADS is here, and this surface is very important. Actually, we pick a particular one for the minimum area surface. Minimum area surface. Minimum area surface. And this is what we call maybe some surface gamma A. But this surface actually plays a very important role. Roughly speaking, the separation between A and B in a quantum matter, some matter here is actually equivalent to separation of space-time, universe, anti-digital universe. So its separation is given by this surface, right, inside and outside. And then what we can find is that this amount of entanglement, correlation between, is actually called entanglement entropy, as I mentioned. This entanglement entropy is, maybe, let me write here. So entanglement entropy is actually turns out to be area of this surface, actually, and divided by 4 Newton constant. This is a Newton constant. I mean, describes how much gravity is strong. And this very simple formula, this is very similar to also black hole entropy formula, actually gives answer to the question that what's the quantum, how much there is a quantum entanglement in this quantum matter between A and B. So this gives a very simple math, geometrical formula. So this is a way how to understand quantum entanglement in ADS-CFT, and also this is related to string theory, as already mentioned. ADS-CFT is highly related to string theory.
Yeah. And so we basically have a duality, right, between this space that we call anti-de Sitter space, or ADS, which is kind of a space with a negative curvature. And the other side, we have a quantum field theory on which we can describe things like entanglement, and we have this duality between them, right? And then, yeah, and so I guess mathematically what we can do is by taking a limit to the boundary of the ADS space, you kind of go to the theory of quantum field theory.
Exactly.
Yeah, so that is very nice. So what do you think we can learn about gravity from entanglement entropy?
Yeah, so this formula, so we have this simple formula. So entropy is area. Entropy is area. This suggests that actually, if we think about this surface which I wrote it here, so far this actually Newton constant, basically you can think some Planck length, something called minimum length in gravity is called Planck length. It's extremely small length scale. In 4 dimensions, this is square actually. So we can decompose this surface, minimal surface, into small cells like this way, with length Planck, this is Planck length scale, tiny scale, and we have a decompose into tiny cells of surface. Then actually for one cell, we have 1 bit of quantum entanglement, and each cell actually also same way have a 1 bit of a quantum entanglement. So we have some entangled cube, minimum entangled qubit quantum bits for each cell. So this suggests that space-time actually, so this surface can be, you can move this surface any location of the space-time. And everywhere in the gravitational space-time, we expect some qubits are sitting and they are entangled with each other. So that suggests that space-time is a kind of collection of this infinitely many qubits, quantum bits, or quantum information. And so this is actually a new idea, and that suggests that actually microscopic, from the microscopic viewpoint, actually gravity is related to dynamics of quantum bits. So this is this actually a way to change our idea what gravity looks like, and it's quite useful to go next step. For example, if we think about not just the anti-Dojita space, which I mentioned. So holography is defined for anti-Dojita space. This is called ADS CFT correspondence. But in realistic universe, we have an expanding universe. And that is one very good example is a Dojita space. Dojita space. And to understand Dojita space, for example, we need this holographic idea, but still we don't know. But actually, we can use this idea. So this universe actually consists of many infinitely many number of qubits, then there is some idea to build space-time, include more general space-time, including Dojita space. So that way, I mean, to generalize this whole idea of holography to more general space-time, I think it's quite useful. This idea of quantum entanglement and the relation between gravity and quantum information is quite important. And there are another one more concrete example these days. This is about black hole information paradox. And recently, there are, very interesting, surprising developments in this subject. So black hole, we have some black hole. If we think some black hole, it is well known that it radiates, so-called Hawking radiation. It radiates and eventually shrinks and just disappears. This is called black hole evaporation. And in that process, it just disappears. So we have a black hole, but in the end, it's just nothing. Evaporates because of this radiation. And but in the black hole originally includes a lot of huge information, because we know this information amount of black hole is estimated by black hole entropy. This is again described by area of this black hole divided by 4G Newton constant. This is a very famous Bekenstein-Hawking formula, and a huge amount of information is included in black hole. So black hole is formed by absorbing many stars, for example, that with already the information of stars, which is quite huge, is included here, and it's very complex a lot. But this information, if we look this way, then because of the evaporation, maybe information looks like disappear, because radiation, we can measure radiation, we can pick up radiation, but it looks random, thermal random state. So it looks like, naively, it looks like black hole is, black hole actually, if we think of evaporation, black hole, the information seems to be lost. This is a huge problem because we believe quantum mechanics, and if we think quantum mechanics is applicable to problem of quantum gravity, this kind of information loss should not happen. So this is called, in physics, this is called unitary process. So if we assume a unitary process, then there are no information loss. So this is a kind of paradox. This is originally raised by Hawking, but recently there are some very important hint to how to resolve this problem. So this is actually obtained by thinking this holographic entanglement I mentioned. So by generalizing this holographic calculation of entanglement, including quantum collections, we can actually estimate how much information we can recover from the radiation. And people showed that there is some special feature called page curve. It's going up. Entanglement entropy between black hole and outside is increasing initially, but in the end going down. So this means that because going down goes to zero, this means that the information can be completely recovered. So if we assume holography and this holographic entanglement as generalization, we can actually confirm that information loss will not happen. So this is, I think, huge, also important development these days, which origins from entanglement.
So if you would ask a question other way around, what can you learn about entanglement entropy or quantum field theory in general from gravity?
Thank you for the question. Yes, so on the other hand, so actually this is actually how to use ADS-CFT. This is a question related to how to use ADS-CFT. And interestingly, ADS-CFT, as I mentioned, it relates gravity on anti-Toshita space to some quantum field theory on the boundary, but there's an interesting connection. When gravity is very simple, like general relativity, so we know how to calculate things using some textbook, the general relativity textbook, and sometimes we need some little bit complicated numerical calculation, but still it's durable. So this general relativity calculation actually is related to a very strongly coupled gauge theory. On the other hand, weakly coupled gauge theory, which is very easy to analyze, actually related to very quantum gravity, which also looks difficult to analyze. So that way, there is some opposite kind of nature. I mean, one side is easy, then other side becomes very hard. So that way, actually, we can deal with very strongly coupled quantum field theory. We can using gravity side. So that actually is, in general, quantum field theory with very strong coupling is very difficult to analyze, like QCD and so on. We need a very heavy numerical calculation based on, for example, lattice gauge theory and so on. But gravity gives some very short answer to some of the problems. Actually, that is actually very useful input. And especially these days we learn that the theory, quantum field theory, which described by Einstein gravity, has a maximum, it corresponds to some maximally chaotic theory. So it's the most, because of strong interaction, it shows maximally chaotic behavior. So we can actually access the maximally chaotic theory. So otherwise, it's quite difficult to calculate many things. So these are actually very good application, how you use ADS-CFT to analyze strongly coupled quantum field theory.
So I find it quite remarkable that we find all the dualities between quantum field theory and gravity. And specifically, I find it quite remarkable that we can find a duality between information and gravity. So considering that information is also a bit of an abstract notion. So you could then almost ask an almost philosophical question like, what does it actually mean that we have this duality between gravity and information?
I see. Yeah, this is actually a bit difficult question, and also maybe answer depends on who you ask. But let me suggest one of my opinion that so holographic relation between, I mean, for example, ADS-CFT or some more general situation suggests that gravitational spacetime is related to collection of quantum bits or quantum information, as I mentioned. So this actually, if we look, this idea is more details, and if we look more optimistic, if we go to more optimistic side, then that suggests that, so if we start with some gravitational spacetime, including maybe our universe, and if we try to magnify some small tiny region, especially the region whose length scale is Planck length. Planck length is a very, very short and minimum scale in gravity. So if we try to magnify the region which is order Planck scale length, then what we expect is that actually we see some kind of qubits. So if we have some ideal microscope which you can magnify just space-time, then this connection suggests that we will see some kind of qubits, quantum bits, so 1 bit or 2 bits like this. So this is what this whole picture suggests. But of course, we don't know the more details. But it's much like we see some atoms from, by using electronic microscope, we can see atoms inside of these crystals. So this, I think maybe something similar can happen. So that is a very interesting, exciting subject.
So what properties of entanglement entropy or particles do you think are specifically interesting to study in holography, and why?
Yes, so there are many interesting properties of entanglement entropy, but maybe I can point out the dynamical property when we think about excited states. So we have start with some vacuum state, but we can put some external force or inject some energy, then we reach some excited states. And it is quite interesting to ask how much entanglement entropy changes if we excite the system. But there is a very nice rule which governs this kind of non-trivial process, dynamical process. This is called first law of entanglement. So in thermodynamics, we know there is a basic thermodynamical law. So first law and second law, zeroth law, and so on. But entanglement entropy also have this kind of thermodynamical law, especially first law. That means that when we excite some system, subsystem, then entanglement entropy also increases some amount. And this amount is actually governed by this first law of entanglement entropy. But interestingly, if we combine this idea, this fact, with ADS-CFT correspondence, holography, then actually this first law of entanglement, which is just a quantum many-body dynamics, is actually mapped to perturbative Einstein equation. So actually, when we have some space-time anti-de Sitter space, but small gravitational waves, this small gravitational waves should follow, of course, Einstein equation, which is a dynamical equation, most important dynamical equation of general relativity. And if this gravitational wave is very weak, then this equation, Einstein equation, is equivalent to this first law of entanglement entropy. So I think this is quite interesting because it relates gravitational dynamics to quantum dynamics, quantum entanglement dynamics. That's, I think, one interesting topic, one direction. We can think about more different excited states and many situations appear. Many interesting situations appears for that. And also another thing, maybe extension of ADS-CFT to more general spacetime. Maybe I mentioned, such as de Sitter space or flat spacetime. So for such when we extend this holography to more general spacetime, we need some basic quantity to calculate. And I think this entanglement entropy provides this, most basic quantity, because entanglement entropy basically captures the degree of freedom of given quantum system. And that means that actually gives a hint of how equivalent gravitational spacetime looks like, and it's how much size it is, and also what's the shape of this universe, and so on. So these information are all included in entanglement entropy. So that way, so when we would like to extend holography to more general spacetime, entanglement entropy plays a very important role.
Yeah, so holographic entanglement is already been around for quite some time. But looking at some more recent research, I noticed that you also did a lot about pseudo-entropy. So maybe you could explain to us what is pseudo-entropy and why is it interesting to study? And also what can we learn from pseudo-entropy that we could not learn from the regular holographic entanglement entropy?
I see. Thank you very much for the question. So pseudo-entropy is a kind of one natural generalization of entanglement entropy, so that it depends on two different states. Entanglement entropy is defined for a single quantum state and measures the amount of quantum correlation, as I mentioned, between two regions over single states. And when we define pseudo entropy, actually we have in mind post-selection procedure. That is, we start with some initial state, some state maybe psi, and then after that, after some time, it's projected to another state phi, for example. So this kind of post-selection process we have in mind, and in the quantum mechanics, just single state, some quantum state is described by a density matrix. But if we think about post-selection procedure, there are two different states appears. That means we have to generalize density matrix into so-called transition matrix. And actually, so this pursued entropy is a kind of entropy for this transition matrix. So this entropy is very simple. It's simply defined by so-called von Neumann entropy minus trace rho log rho. Very simple formula. Very simple formula. But we just this rho is a density matrix in usual entanglement entropy. But we replace this with so-called transition matrix tau. So this is how we define pursued entropy. And the good thing of pursued entropy is that actually it naturally arises in the context of ADS safety correspondence. So if we think about ADS safety correspondence and in Lorentzian space, time-dependent background, so you have some, we have some state and we have some, for example, energies injected, then it's non-trivially time evolved like this way. And in that kind of Lorentzian setup, actually we can compute entanglement entropy by looking at extremal surface. In time-dependent case, we need to use, instead of minimal area, but we need something called extremal surface. But anyway, so this works very well. But if we think about Euclidean time-dependent background, Euclidean time-dependent background means time is imaginary time. Imaginary time appears, for example, in quantum mechanics like that. If we think about process like tunneling effect, it's one state goes to other state, tunneling effect. Then imaginary time appears. In physics, imaginary time is also heavily used. Also to describe, for example, finite temperature system, thermal system, imaginary time appears. So this is not nothing special. And if we think about the imaginary time-dependent background, then actually initial state and final state is different. Like this, like this post-selection procedure. So we start the initial state and project to other state. This actually happens in Euclidean time-dependent background. But the Euclidean time-dependent background, we can still think about minimum surface, minimum area surface. And if we calculate this area, it turns out, interestingly, it turns out that this quantity is no longer entanglement entropy because we have two states are involved. So actually this quantity, this area, minimum area, turns out to be equal to pursued entropy, which I just mentioned, like defined using transition matrix. So this is a very interesting thing. And also one more thing is actually, if we think about Dojita space, I repeatedly mentioned Dojita space, instead of anti-Dojita space, so Dojita space looks like this kind of expanding universe. So we start with some small universe and exponentially expand. Maybe you can put some tunneling effect here, but it's expanding universe. And then in this case, if we apply holography, boundary is here. Boundary is far future. It looks like space like far, right? And then we calculate holographic entanglement entropy. It's like this way. It's good vertically actually. Go vertically. That means this is a timeline. This is a real timeline. And that makes this holographic entanglement entropy becomes complex value. I mean, there are imaginary parts to holographic entanglement entropy. And if we also remember, if we go back to pursued entropy is defined by transition matrix. And transition matrix is in general not Hermitian. So that makes pursued entropy also in general complex values. There are real part and imaginary part. And actually, we find that we can find that this Dojita, holographic entanglement entropy in Dojita space actually should be more correctly interpreted as a pursued entropy. So that way, if we go beyond ADS-CFT, more general spacetime, actually pursued entropy is quite common thing and often appears in natural way. So this is the reason why we are interested in this pursued entropy.
Yeah, so in also your latest article, you explore entropic quantities that can be applicable to this post-selection process that you already quickly mentioned. You propose a new quantity based on a singular value decomposition, or SVD, of the transition matrix that you also mentioned. Could you maybe elaborate on what this SVD entropy is and how it is applicable to the post-selection process?
Okay, thank you very much. So this SVD entropy actually kind of some deformation of pursued entropy I mentioned. Always we start with post-selection procedure. We have two different states, initial state, final state, and we define transition matrix. It's just kind of transition matrix because it's not Hermitian because these two states are different. If we take a conjugate, it's like we flip these two and they are not equivalent. So anyway, because of that, pursued entropy becomes complex value that I mentioned. But the problem is that it is naturally motivated by ADS safety. And if pursued entropy is real, then it have a nice interpretation in terms of classical geometry, like time-dependent antidocital space. This is nice. But if pursued entropy has an imaginary value, to be honest, we don't know how to interpret this imaginary part so far. It might be very interesting, but so far we don't have any intuition or any quantum information theoretical argument how to interpret the imaginary part. So another approach to this kind of problem, maybe think about some other quantity which don't have this imaginary part. So this is motivated by this, we introduced this new quantity called SVD entropy. This is actually, again, of course, based on transition matrix, but first diagonalize transition matrix into eigenvalue, real valued eigenvalues by using singular value decomposition. And once we have a non-negative eigenvalues, then we can define so Shannon entropy. These are basically the same as von Neumann entropy, which I mentioned. And then this is a really nice quantity, like it's always non-negative. And it looks like an entropy quantity. But as opposed to pursued entropy, its connection to holography is not so much clear. But anyway, it has, again, interesting property that if we calculate this SVD entropy in terms of SVD entropy in a quantum manifold system, like spin chain, various spin chain, we find that actually SVD entropy is a nice new quantum order parameter of different quantum phases. We can distinguish, for example, ferromagnetic phase and paramagnetic phase in transverse sizing model like that way. So SVD entropies can be used also as a kind of quantum order parameter. So I think this is also interesting quantity. And also one more thing, SVD entropy has a nice interpretation in quantum information theoretical consideration. So SVD entropies, again, we start with the initial state and final state, and there are intermediate states between that. And that we can actually see that. So SVD entropy counts number of Bell pairs, entanglement pairs, which appears in the intermediate state. So we usually use some language called some distillation or LOCC to extract number of qubits. This actually we can say there is a very famous fact that known in quantum information theory, we have some quantum system, quantum pure state, and we have A and B, like the setup of entanglement entropy. So we have two A system and B system, and counting number of Bell pairs, entangled pairs. This average number precisely agree with entanglement entropy. This is actually motivation why we consider entanglement entropy. And similar statement can be found for SVD entropy. That's another advantage.
Mm-hmm. Yeah, so you maybe mentioned a little bit, but can you emphasize what makes this entropic quantity so intriguing?
Yeah, so already mentioned, but I think anyway, it is a non-negative. It's a quite well-defined quantity, and we can study it in explicit quantum systems, and it can be used for as some quantum order parameter. And also, actually, this can be applicable to non-equilibrium system, some open system, where in general we have some non-unitary dynamics, and we encounter, in some formulation, we encounter some non-Hermitian density matrix. And in that case, we can, even if the theory is non-Hermitian, we can still define some sort of entanglement and by using SVD entropy. So I think this part is quite interesting to look at.
Yeah. So are there any other results from your, maybe recent results from your research that you like to point out?
Okay, so thank you for the question. Maybe I would like to mention another topic, which is actually related to this black hole information paradox, but another topic is a quantum field theory, which lives on the boundary. So a manifold with boundary. So quantum field theory, usually we consider quantum field theory lives on a compact manifold without boundary, but sometimes it's quite interesting to think about some quantum field theory which lives on the boundary, like this. And boundary. So for this actually, we can generalize ADS safety to, this is called actually ADS BCFT, but we can generalize holography to this kind of setup with quantum field theory on some manifold with boundary. So the new thing is obviously boundary. So to construct holography, we have some anti-Doshita space here in this direction, but also we extend this boundary towards the bulk ADS. So this is a new ingredient. This is called end of the world plane. So really, world is end here. So nothing here. So anti-Doshita space originally extend to both sides, but we introduce this. We cut the area space into half and only pick up this side. So it's really end of the world here. So this is actually, this end of the world brain have a very interesting dynamics. This is why this subject is quite interesting. So these are some brain here. We have about brain which extend into the ADS, and they have some dynamics. They can, for example, oscillate and so on. So that means that actually their lower dimensional gravity is localized on this end of the world brain. So this means that there are QFT, quantum field theory, but it's also we can regard this as some quantum field theory coupled to some lower dimensional gravity. And if we introduce, for example, black hole in this in gravity side, then this describes some Hawking radiation, and Hawking radiation is captured, probed by this quantum field theory. So this is a nice setup to study black hole evaporation process. And this is heavily used. And the interesting thing here is a calculation of holographic entanglement entropy. So if we want to calculate entanglement entropy using ADS-CFT, so we have like this. So we have this kind. This is the anti-Doshita space, original anti-Doshita space, and we cut into this like this way. ADS space-time into this way. And if we want to calculate some minimal surface, so we take this region A here. The minimal surface usually looks like this, but new thing, this minimal surface can now end on the end of the world brain, like this way. So this guy is the end of the world brain. This blue guy is the end of the world brain. End of the world brain here. And this minimal surface can end on the end of the world brain. This is a new issue. And this is actually how this information paradox can be resolved. Actually, in the what I mentioned just a little bit before. So to derive some behavior called page curve, this is very important actually. But this means at the same time, this means that so there's a gravity here. So we have a gravity, but actually the gravity, but only in this region. If we focus on this region can be probed by outside observer, even if this observer is outside of black hole. So that way, so somehow information can be go out of black hole through kind of wormhole. So this is what we find for this entanglement analysis of entanglement entropy with in a manifold with bound. So this is has an interesting applications. This is maybe the thing I wanted to mention, an extra interesting subject.
This is the solution to the information paradox.
Yes, information paradox. Yes, at least it gives a very important hint. So information paradox appears because we cannot extract inside black hole information, but black hole just disappears. So even before this, we extract information inside the black hole. But actually, inside this information inside the black hole is actually accessible to outside observer even before, much before black hole evaporates. So this picture basically shows this kind of effect.
Nice. Okay, so so you clearly do a lot of work with string theory. So why, in your opinion, is string theory or holography the most prominent theory of quantum gravity? Or like, what are the strong points of holography or string theory compared to other theories of quantum gravity?
I see. Yeah. So I think anyway, the strongest point of string theory and holography is that, as shown in a famous work by Strominger and Buffer. So black hole entropy was derived, using string theory, and in a microscopical way. So we know how black hole entropy looks like. It's an area formula which I mentioned before, but we can microscopically derive it by using counting of number of states in string theory. But this actually also later developed into this ADS-CFT correspondence. It's kind of one example of ADS-CFT. And the ADS-CFT is so successful, it's tested by many thousands of papers. And also it fits nicely with this quantum information idea and also other applicable to non-equilibrium dynamics. And always we have nice results. And also really quantitative matching we can find many times. And so that suggests that string theory is a very successful candidate of quantum gravity. And as far as I know, I cannot find any other candidate of quantum gravity which are so successful to understand some quantum gravity. And maybe also you asked about some problem of string theory, also flow.
That's the next question.
Okay.
Yeah, the next question is like every theory has its problems and flaws. So what would you say are the biggest flaws and open problems in string theory and holography?
Yeah. Okay. So that is actually, I think it's a kind of technical issue. So string theory, so main technical problem of string theory is string theory is heavily rely on very deep mathematical structure. So this, of course, that means theory is very well organized. But at the same time, if we accept some simple example, in general, it's quite difficult to analyze string theory in detail. For example, in flat space, we know how to calculate scattering amplitude in string theory. And the anti-Doshita space, we know we can apply ADS safety to relate quantum gravity on anti-Doshita space to some quantum field theory. This is very, very good. We can have a non-perturbative description of the quantum gravity on anti-Doshita space by using ADS safety. This also originally comes from string theory. But what about more realistic universe like cosmological universe like Big Bang singularity or Dojita spacetime, which is very important in the current universe and also inflation theory. So actually, for example, Dojita space is very difficult to analyze because we know that we need to combine many different ingredients of string theory. So that makes analysis very complicated. So and also this is a reason why holography for Dojita space is very difficult to understand. But I think this, in the end, we should resolve this issue. But I just want to mention that string theory has a very supported by very heavy mathematical background. So that actually is cause many technical problems, and which we need to understand better in future works.
So what are currently some very trending topics in holographic entanglement entropy, or some open questions in holographic entanglement entropy that future generation of researchers can work on?
Yeah, so I think one interesting new trend of this entanglement related topic is algebraic approach, operator algebraic approach, which is very mathematical. It's some theory of von Neumann algebra. And so in mathematics, actually, entanglement entropy in quantum field theory is not well defined because it has a UV divergence, ultraviolet divergence. In physics, we usually impose some lattice regularization, and make it finite, as we do when we talk about renormalization and so on. But anyway, it is not well defined in mathematics. But actually, interestingly, if we couple this quantum field theory with gravity, then situation changes because there is as appears in many times in my comments, that gravity has its own entropy, gravitational entropy, like black hole entropy, also holographic entanglement entropy, it's area law entropy. And this area law entropy always includes Newton constant, area divided by 4 times Newton constant. And Newton constant is a coupling constant. It should be renormalized. So this Newton constant renormalization and this divergence of entanglement, this is called area law divergence. Also, this is proportional to area, actually. This is a very important fact. But the entanglement entropy divergence, actually, they can cancel, assuming some renormalization gravity. So that way, somehow, if we couple quantum field theory with gravity, so actually, even mathematically, this entropy becomes well-defined. This fact is recently heavily discussed. And in the end, we want to promote this to full quantum gravity. This is a very interesting topic discussed by many people these days. And maybe, so this idea gives a more concrete interpretation of idea of this emergent spacetime from qubits. Or sometimes we call it from qubit. It means this whole universe is made from qubits. But we don't know what qubits precisely means. But maybe using this mathematical idea, if we understand this Hilbert space of quantum gravity better, then we can really identify what this qubit means. in mathematical sense. So I think that's quite an exciting subject, which is also discussed by many, physicists these days.
Yeah, so interesting things for other people to work on. So thank you for this nice interview. So I'd like to still ask 2 questions, which I usually like to end with. So first question is, why did you personally choose to study quantum gravity, and what do you love most about quantum gravity?
Okay, yeah, thank you for the question. So anyway, I have been, since when I was a graduate student, I have been quite interested in fundamental theory of physics, not only related to gravity, but also, many quantum gravity issue, but also including some, more particle physics also theory. And but in the end, I find that quantum gravity is the most outstanding, unsolved problem, because it's extremely difficult compared to other theory, and also it is more, most fundamental theory, because it involves with some really deep question, like even philosophical deep question, like what's the beginning of universe, how universe begins, and also maybe, for example, how maybe time also gets emerges from the birth of universe. So how time emerges from out of nothing. So that's kind of very deep question, is always related to quantum gravity. So that's the main reason why I'm working on quantum gravity, and very much so I'm extremely fascinated by this topic.
So last questions. Do you have any advice or wisdom for young quantum gravity students or people who want to study quantum gravity?
Yeah, so as we see from this recent development, it often happens that this, ideas or even recent progress of other subject like quantum information theory or condensed matter theory. Now, initially we don't expect these are related to theory of gravity, like quantum gravity, but actually these ideas are quite useful in the recent development of quantum gravity. So I'd like to suggest young researchers who are working on quantum gravity to look into and get interested in this subject, which is not exactly gravity, but closely, in the end, maybe closely related subject, like in an interdisciplinary way, like including this whole theoretical physics, whole physics, and also quantum information and mathematics, and also maybe many more. So I think it's quite a good idea to make everything in interdisciplinary ideas, and like keen to some development of other subjects.
Thank you very much. Also, thank you very much for this interview. It was very nice talking to you. And I also look forward to see more about holographic entanglements in the future.
Thank you so much.
And for everyone at home, thank you for watching and have a nice day.